In our next unit, we will study chemical kinetics, which can be found in Chapter 14 of your textbooks. Chemical kinetics involve the topics of reaction rate, rate laws, and reaction mechanism. The purpose of this video is to introduce you to reaction rate and rate laws. Reaction rate is just what it sounds like. It's how fast a reaction occurs. Evidence for this is the change in the amount of reactant or product as the reaction proceeds. Think about what we can measure in the lab to indicate reaction rate. If we were collecting a gas over water at constant pressure, we could measure the volume of the gas produced. If instead we were using a constant volume reaction vessel, we could measure the pressure of the gases produced. In general, though, we will just talk about the concentration of products and reactants in moles per liter. Consider the reaction between gaseous nitrogen and gaseous hydrogen to form gaseous ammonia. We could talk about this reaction rate in terms of the moles per liter of nitrogen consumed per time, or the moles per liter of hydrogen consumed per time, or even the moles per liter of ammonia produced per time. If we think about it, the rate of consumption of nitrogen and hydrogen and production of ammonia should be related by the stoichiometric coefficients in the balanced equation. Considering kinetic molecular theory, several factors should impact reaction rate. First of all, reactant concentration. It's less likely that reactants will run into one another to break reactive bonds and form new product bonds if there's less reactants per liter. Similarly, collisions are less likely at a low temperature, more likely at a higher temperature. In addition, at a higher temperature, collisions are more likely to have sufficient energy. A catalyst increases the likelihood of a successful reaction by offering an alternative pathway with a lower activation energy, such that a higher portion of the collisions are effective. Generally, we will be considering reactant concentration as the factor that most impacts reaction rate. Consider the graph below that plots reactant concentration versus time. As a reaction proceeds, the reactant concentration should decrease. Taking note of the graph I've just drawn, this reaction has a constant reaction rate. Hint, the slope of the graph is the reaction rate. But what should be happening to the rate as the reaction proceeds? Well, as there's less reactant available, we should see a slowing of the reaction rate. So in general, a graph of reactant concentration versus time looks more like the second or the third graph I've drawn. A rate law is a mathematical equation that determines exactly how concentration is related to rate. If you note in the reaction below, A moles of A plus B moles of B react to form C moles of C and D moles of D. The rate law for this equation might look something like rate equals K times the concentration of A to the M power times the concentration of B to the N power. K is called the rate constant, and M and N are both experimentally determined. In other words, you can only determine the values of the exponents M and N through experimentation. For instance, the reaction 3A plus B plus C yields D plus E might have the rate law rate equals K A squared times C. You might be asking yourself, how does he know that A is squared and not to the third? Or where's B? Or how did he get the exponent for C? But remember, all of these are determined experimentally. We would say that this reaction is second order with respect to A, 0th order with respect to B, and first order with respect to C. Overall, This reaction is third order. We can find the units of the rate constant by considering the remainder of the equation algebraically. If we solve for k, we see that k equals rate divided by the concentration of A squared and the concentration of C. Unit-wise, that means the rate constant is equal to molars per second divided by molars squared divided by molars, which simplifies to 1 over molars squared seconds. One type of problem you'll face in this chapter involves concentration and initial rate. These are called initial rate problems. You'll be given data about the concentration of reactants, say reactants A, B, and C, and some information about the initial rate of the reaction at those concentrations. Basically, what you'll do in these problems is look to see what happens when the concentration of A is changed, but B and C remain constant. If the concentration of A doubles and the reaction rate remains unchanged, you know that the reaction rate does not depend on the concentration of A. Similarly, if the concentration of A is doubled and the reaction rate doubles, then you know that the reaction is first order with respect to A. If we were to triple the concentration of A and the reaction rate were to go up by a factor of 9, we would know that the reaction is second order with respect to A. Another type of problem you'll face in this unit is similar to the graphs of concentration versus time we looked at earlier in this video. You'll be given data about concentration and time and asked to find things about rate and rate laws. Let's start by considering a reaction that has only reactant A, or at least only reactant A that we care about. The rate of that reaction will be given as negative change in concentration of A versus change in time. This is true no matter how the concentration of A impacts the rate of the reaction. If, however, the reaction is known to be second order with respect to A, we can also say that rate is equal to K, the rate constant, times the concentration of A squared. I've started with second order because the calculus is easier. Speaking of calculus, you'll never need to use calculus to solve these problems. It's just that the equations we'll use come from calculus. In fact, these particular problems make use of something called integrated rate laws because the equations we use are derived through integration. For those of you that care at all where these come from, I'm going to rewrite rate as equal to negative dA over dt equals k times a squared. The calculus then is that we integrate this equation from time 0 to time t, and we get 1 over the concentration of A at time t minus 1 over the concentration of A at time 0 is equal to the rate constant k times t. This is the integrated rate law for a second order equation. If we rearrange this equation, we get 1 over the concentration of A at time t equals kt plus 1 over the initial concentration. Please note that this means if we graph 1 over the concentration versus time, we should get a linear relationship. Moreover, the slope of that linear relationship should be the rate constant. If we repeat this exercise for a reaction known to be first order with respect to A, we'll get that rate is equal to the negative change in concentration of A over change in time, which is also equal to K, the rate constant, times the concentration of A to the first power. When we rearrange this and integrate, we'll get the natural log of the concentration of A at time t is equal to negative kT plus the natural log of concentration at time 0. This would mean that if we were to get a first-order reaction and plot the natural logarithm of concentration versus time, we should get a linear relationship, and the slope of that line should be the negative of the rate constant, K. This page summarizes the concentration versus time using integrated rate laws. If we were to graph the concentration of A versus time and get a linear relationship, well, that would mean that the slope is constant and the rate of the reaction is staying the same. In other words, the rate of the reaction is not impacted by the concentration of A. If that graph is nonlinear, we can graph the natural log of concentration versus time. If that's linear, that tells us that the reaction is first order with respect to with respect to A. Moreover, the slope of that graph is going to be equal to negative K, or negative the rate constant. If that graph, natural log of A versus time, isn't linear, we can graph the inverse of concentration versus time. And if that's linear, the reaction is second order with respect to A, and the slope of that graph will give us the value of the rate constant, K.